All right, ladies and gents, good morning. I want to go through a couple of things about class sort of administrative stuff that I think is going to help y'all in the long run. First off, I have on here to talk about the bell ringer. All right, so let me just remind y'all that that bell ringer is for y'all to practice skills that are going to show up, that are foundational to chemistry, and that you will need regularly or in the future or in physics, in chemistry in college, whatever it is. It's to imprint those things and get you to keep those, um, you know, with you. All right, not to cram and forget, as the publishers of our book here are fond of telling you that they refuse to let you do. But so specifically for the bell ringer, I want you to use your book if you don't know how to do it, and I want you to complete it, and not sort of just bide your time and wait for someone else to work it. Okay, so what I want to happen is that you guys have 5 or 10 minutes or however long it takes, maybe even up to 15, I guess, if we've got some folks who are pushing to get finished still. And then Ms. Barron is going to check and watch to make sure that you guys are actually working that time. But then she's going to make any notes if she feels like she needs to about what is, if it looks like you're not working, she's just going to mark that down, let me know, and you'll have a 0 out of 5. Okay, it's not going to be a huge deal, but it is going to ding you a little bit. So make sure you are working on them. But then she's going to work through them, and I want you to correct them in color pen. Okay, the point is not for me to have you do 5 minutes worth of busy work. Okay, the point is I see some patterns on your tests and on your quizzes and on your homeworks that show me that y'all have holes in how you handle numbers and concepts. And we're trying to plug those so that you don't get bad grades on quizzes, get bad grades on tests, whatever. I also went through, so all I say, bell ringer, you guys take some initiative there, write down what Ms. Barron does, and correct it, and then those will come home with Ms. Anlari, Ms. Forster, and I will check those for basically completeness and correctness, since you will be correcting them. Okay, so you'll have an opportunity to work it. You will not be hurt for not finishing it as long as you are diligent at the time you've been given, and then as long as you correct it in a colored pen, or if you're doing it in pencil, at least in pen, so I can tell what the corrections are. Okay, I'll try to do that, and hopefully it'll just be 5 out of 5 every time, and you'll get to review some stuff. All right. Also, the Asimov commentary. I hope you guys found that at least a little bit interesting. I want you guys to get together to correct that. I will be asking some of those questions, pretty broad questions. Okay, I'm not going to be asking you like what year was cesium, discovered. I'm not interested in you memorizing that. Okay. I am interested in you knowing something like Mendeleev's table predicted gaps, and then they found elements that were plugged into those gaps. Okay, that's a pretty important deal. That's pretty strong predictive power, and it shows how scientific theories can work and be proven right or wrong. All right. So I do want you to get together, make sure you got all your answers right. I don't think I actually went through and marked everything, so maybe y'all just kind of sit around for 15 minutes and make sure everybody's got all the right answers at lunch one day or whatever. All right, but don't just toss that. Those should be coming back to you. Miss Barron should have those and should be handing those back or have handed those back already. So you can take those home and work on them. All right, so really fast, what do we have coming up? You guys have just done your bell ringer for today, I hope. And actually, I probably will just send Miss Barron an email in a minute here, and you guys will be about to do your bell ringer. So y'all pause this and start me back up after you have done your bell ringer. All right, I hope that bell ringer was stimulating. While I'm recording this, though, I haven't written it yet, so it's kind of like we're doing time travel stuff here. You're in the future, I'm in the past, but I'm speaking to you from the past. It's pretty amazing. Now that your mind is blown by time travel, we're going to follow our rubric here and go through and review assignment sheet, and just review your homework real fast. I want to talk you through some of these. 3 is the first one, so if you don't have that out, just go ahead and pause me and get that out. Okay, obviously you've already sent that to me, and if not, make sure you do it as soon as you get home so I can give you late credit. Okay. All right, so 3, state the chief chemical property that distinguishes the metals from the non-metals. All right, so just, flip back. What's it say? Is there just one thing? Chief chemical property that distinguishes the metals from the non-metals. Oh, yeah, that's right. Metals don't bond with one another, and non-metals do. And I'm trying to find where that says that. They also bond with each other, something metals almost never do. And remember, we talked about that. That shouldn't be there. All right. So that's your main deal right there. Okay, that would be a great quiz question. Okay. All right. Distinguish between cations and anions. We'll flip back. And what do we see? Cations, positive ions, anions, negative anions. I would suggest making a note card for those just to keep them straight, okay? Because again, that would be just a great quiz question. All right, 6 through 10. Describe the trend in atomic radius going down a group and across a period. All right, remember what was our deal? Okay, we had our chart here. What was our biggest one? Francium was our smallest one, other than hydrogen, which is always weird. Helium. Okay, so remember, francium big, helium small. That's all we got to remember. Francium's big, helium's small. All right, so let's answer our question. What's the trend of atomic radius going down a group and across a period? So going down a group, francium's big, helium's small, so they're getting bigger going down the group. Okay, and as they go across a period, they're going towards helium, means they're getting smaller. Okay, smaller, bigger, or bigger, bigger. All right. Just no way to get around just memorizing that, guys. So just take a look at those things. You will have to do something with that on your quiz on Thursday. Okay? Knowing that fact that francium is big and helium is small, and what that means when you're comparing, which we're about to look at here. Write a description for accounting for the trends in atomic size in the periodic table. Some good things were would be electrons on the closer to the nucleus, on the inside, closer to the nucleus, shield the outer electrons from that electromagnetic field, meaning that that positive nucleus doesn't pull quite as hard on those electrons, okay? Meaning that they're out a little bit, okay? And then it's why we see each successive row, or better yet, this one will show you better, okay? That's why each one of these is bigger. It's not just because there are more electrons that need to fit in there, although that is true. It's that these electrons on these guys are shielding the next set, which are shielding the next set, which are shielding the next set, okay? All right, so that's kind of the base thing you need to do there. All right, from your knowledge of the periodic table, put the elements rubidium, silver, xenon, yttrium in order of increasing atomic radius. Okay, so what I like to do is I want to do this. Blank, 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 blank. All right, and I want an increasing atomic radius, so I'm going to say bigger. Okay? That takes some of the memory out of it for me. Okay? And so what do we know? What do we say? Francium's the biggest, helium's the smallest. Okay, so what were ours? We had rubidium, yttrium, silver, sorry, just a Y, silver, and then xenon, and xenon. Okay, so what do we notice? Rubidium, yttrium, silver, xenon. They're all on one period. Okay, they're all on one row here. Okay, so that makes that comparison nice and easy. All right, we said this was small, this was big. Remember, big, small. So what's the biggest is on this side? So that's rubidium. And then the smallest is on this side, so that's xenon. Then we have silver and yttrium. Okay, so that should be the order. That should be what your homework looks like right there. Okay, sometimes we could add something like this to be super. That's wrong though. Okay, just make sure you do them right. It's as you can see, it's easy to get them wrong. Okay, a lot more practice in this than y'all are, and it's still easy for me to get those things flopped around. Okay, and guess what? If you flip them around in the quiz, they're wrong. All right. Okay, so that's that. All right, now let's look at our next one. From your knowledge of the periodic table, put the elements sodium, barium, cesium, magnesium. Okay, in order of increasing atomic radius. So again, do bigger. 1, 2, 3, 4. All right, now this one's going to be a little bit different. So what do we have? We've got sodium, magnesium, barium, cesium. Okay. So the trend is big and big. Okay. So what's the furthest down and to the left of all of these? So that's, oh man, I'm messing this up. Cesium. That's CS. All right. So cesium is the furthest this way and the furthest this way, so he's the biggest. Okay. Now we have a question. All right. So sodium's above, which means he's smaller, but barium's to the right, which means he's smaller. Okay. I'm guessing because this guy is 1, 2, 3, he's a lot smaller than barium is small because he's just 1 over. But let's check. It says use your knowledge, but we can go check. We don't have to guess now that we're looking at our homework. What are we comparing? We're trying to compare sodium and barium. So let's look at this. We've got sodium, and then barium is right after cesium. So cesium, all right, so here's barium, and here's sodium. So barium wins, like we thought, because he's only 1 away, and so only 1 smaller, while he's 1, 2, 3 smaller. All right, and then so of these two, which one's smaller? Which one's bigger? Sodium's bigger because it's big and big. So big is that one, and then magnesium is there too. Okay. All right, so you can see there's a lot of thought that needs to go into these. Okay, and a little bit of strategy for how you manage your knowledge there. All right, so don't rush through. So you get some very simple principles that push you towards the right answer. Okay, don't freak out. Just figure out which one's the furthest to the left, which one's the furthest towards the bottom, and that's gonna figure it out for you. Okay, all right, last one. Wait, hold on, what was that? That was 8 and 9, right? 8 and 9. All right, last one we're going to do is 10. Okay. Based on your knowledge of trends, place the following atoms and ions in an order of decreasing size. All right, so decreasing size. We want to go, what's this? Smaller. Okay, so y'all read carefully. All right, Be2+, and remember what's that 2+ means. What does that 2+ mean? Okay, means we've lost 2 electrons. Okay, they've left, leaving a +2 charge. Okay, magnesium, calcium, magnesium 2+. That's not a 2T, it's just a 2+. Okay, so let's reestablish our principles in our minds, right? So what happens? The regular is blue, the ionic is yellow, and this one is a +1, which means lost 1, so which makes sense. It loses 1 and it gets a little bit smaller. Okay? Whereas the minus is the regular, the neutral one is the blue, and as they become a -2, they gain 2 electrons, so poof, they fill out to take those electrons in. Okay? So if you're losing electrons, your ion is smaller, and if you're gaining electrons, your ion is bigger. All right, so let's keep that in mind as we look right here. Okay, so what do we have? We've got beryllium, 2+, magnesium, calcium, and magnesium 2+. Okay, so remember, they get bigger this way. All right, so I'm going to say that calcium is going to be my biggest. Okay, and then that beryllium 2+ is up, which means it's going to be small, and it's a 2+, which means it's lost 2 electrons, which means it's going to be even smaller. So he's going to be for sure right here. Okay. So as we go down, we get bigger. Okay. So as we go up, we get smaller, and so that means our magnesium is smaller than our calcium. And then if we take 2 electrons away, it gets smaller still. Okay. Here's our normal, the blue. And then we take 2 away from it to make it a 2+, and see how much smaller it is. Okay, so that's right. So in order small, we should have that magnesium, and magnesium 2 plus. Okay, so again, simple principles. All right, we got what? Francium and helium. As this is the big guy, atomic radius wise. And then we have, if you remove electrons, the atomic radius shrinks. Okay. If you remove air from a balloon, it shrinks too. Okay, so that's pretty intuitive. Okay. Now, we'll come back to some of that just to reinforce that. Okay. All right, so I want to take you through the first part of 4.4. I should have told y'all to only read the first half of that. It's too much to really go into. So I apologize if you read the whole thing, but you'll be just super doubly prepared forever for the next one. But we're only going to go through core and valence electrons and then ionization energy, because you can see how much stuff that's going to take all the way through there. And then we'll go into electron affinity after your quiz, and electronegativity after your quiz, and a few notes about hydrogen after your quiz. Okay, so we got a pretty heavy chapter here, content-wise, which is why we're going to take two full days to go through just this section. And your quiz is only 4.1 through 4.3. Okay, it's too much to try and push that into 4.4 or to give you a quiz on the whole chapter. So we'll do 4.1 through 4.3, and then we'll have a test on chapter 4. Let's see, where are we? Let me shrink the little screen here. We got a while before test on chapter 4 because we got to do an experiment in there too. But we will have a test on the 30th, okay? And that'll be nice. You can have Halloween, and you'll be done with your chemistry test. That'll be great. Okay, hold on. All right, now, all right, let's get into it. We're 22 minutes into our recording and hadn't even started on our content. All right, section 4.4. Make sure y'all got your books out, please. Okay. All right, core and valence electrons. All right, this is a topic or a subject, a bit of knowledge that you really need to get clear on, okay? Because we talked about in the very introduction, or rather the book talks about, and your previous teacher may have talked about, almost all of chemistry is only worried about valence electrons, okay? The core electrons really don't get messed with a whole lot, and we'll see some of the ionization energies will kind of point us, give us a little hint in that direction that they, why they don't get messed with very much. But let's talk about what they are, okay? So back to what we learned before, electron configuration, right? Sulfur, look at it on your periodic table there. 1s2, 2s2, 2p6, 3s2, 3p4, okay? All right, 1s2, 2s2, 2p6, 3s2, 3p4, okay? We beat that into our heads last couple of weeks, so you guys should be pretty familiar with that. I took a test on it. But green, basically, are your core electrons. Yellow are your valence electrons. Core is the one on the inside. Valence are the unfilled shells on the outside. Okay, so if it's full, we're going to call it a core electron. Or if that shell is full, it's going to be full with core electrons. Okay, so greens are core electrons. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 core electrons, and then 6 valence electrons. Not super complicated. Okay. Note your definitions here on page 108. Going to be important. All right. Also note that right here, okay, what you write in the condensed electron configuration, what this represents is neon. Core, what represents and comes after that are your valence electrons. Okay. All right. Note cobalt here. A little bit different situation. They're not both in the 3 period. Okay. It's got 4s2, 3d7. Okay, these are called valence electrons, even though, as we'll see in a minute, usually it's going to prefer to mess with these, not with these. Okay, but we'll get there in a second. All right, hopefully everybody's clear on that. It's pretty straightforward. The stuff above the last row of electrons that it has full are core, and the stuff on that row are typically the valence ones. Okay. And if you think of it like a castle with moats and people in between those successive moats, and you have invading people. Who are they going to go after? Well, they're going to go after the guys who are outside the outermost moat. They're not going to pass those guys up and try and get past them, cross a moat, come in to kidnap these guys. No, they're going to take the easy pickings on the outside. Okay, that's what's going on with core and valence electrons. Okay. What else? All right. Finally, note that for p-block elements in periods 4 through 7, the electrons in filled lower d subshells do not act as valence electrons. Okay. So these are valence. These are not. All right. I think he does a pretty good job of illustrating that. All right. We're just going to push on, and if you guys don't understand it, we'll let Ms. Barron pause and talk to you about that. All right, so one way we can think about whether electrons want to leave or not, we talked about before ionization energy. That was one of the first things we talked about. One of the first things you guys and I talked about. Okay, just kind of jumped right into it. Because we were talking about it in terms of how much energy does one quanta of a particular light wave donate into an atom. Okay? And we talked about that energy in terms of what would it do to an electron here. And if it does give it enough energy, it can even ionize that electron, and that electron would come from its normal state and go all the way up to 0 joules and leave orbit, as it were. That's not the right way to think about it, but it's a helpful way to talk about it sometimes. I'm sorry. The quantum stuff's just too weird to really talk about and give you an intuitive sense of it, okay? All right, so sometimes the energy that's required to ionize comes in the form of light or electromagnetic radiation, sometimes visible light, sometimes gamma or X-rays, okay? That can ionize things, all right? But sometimes ionization comes in the form of an electric arc or in a lot of heat or whatever. Any way to get that energy into that atom can ionize an electron, okay? All right, now, using hydrogen as an example, the removal of the electron from an atom of hydrogen is modeled using this little equation right here. So what does this say? Hydrogen as a gas. Okay, things are a lot more easy to ionize when they're gases, just because the atoms are so much further apart, or the molecules are so much further apart. Okay. So often you'll see this hydrogen as a gas. That's just referring to literally the physical state. All right, it becomes hydrogen plus and 1 electron minus. These guys have now been separated. Okay? And then it just tells you that's the energy it took to do that. That's nothing special there. It's just saying the change in energy is this many joules. Look how small it is. Times 10 to the negative 18th. 0.000000028. Okay? All right. Because the amounts of energy involved in ionization are so small, it's more convenient in these discussions to use a sort of energy unit called the electron volt. Guess what? We now have a new unit that you guys need to know what it is. Mark it in your book. Mark it. 1 electron volt is this. Okay? So if you are converting, for example, and you had 2.15 times 10 to the negative 15 joules. And I ask you, how many electron volts is that? What are you going to do? You're going to say, oh, look, I know a conversion factor. Okay, we got to get rid of joules. 1.602 times 10 to the negative 19 joules is 1 electron volt. Okay, what's that going to cash out to at the end of the day? You're going to take that in your calculator and divide it by that. Okay, and you're going to get some number. It's going to be 1 point something times 10 to the 4th electron volts. Okay, and I'm just guessing based on these. Okay. Easy peasy. Follow the same method we've used before, okay? So he's showing you, oh, look at that, 2.15, 2.18, whatever. All right, you got okay, except he uses negative 18, not using negative 15. Okay, same deal. All right, I just use the little cancel out thing, and he's just showing you how you multiply. Okay, so it gives you the number of electron volts right there. Okay. All right, another term that's going to be useful. Oh, pardon me, guys. We're going to remove 1 electron from a neutral atom. So to take oxygen from oxygen 0 to oxygen 1 minus would be called the first ionization energy. Okay. Oh, that was a bad example. Removing an electron. So we're going to go from, say, lithium to a lithium 1 plus. Okay, because these guys on this side of the periodic table like to lose electrons and these like to gain electrons. So these get a plus charge. Okay, so that would be its first ionization energy, and then the additional energy required to remove a second electron is called the second ionization energy, and so on. Okay, so remember, ionization is removing those electrons. All right. Let me go ahead and introduce this part. I'm going to flip it forward 1 page. Okay. Electron affinity is defined as the amount of energy released when adding an electron to the ground state isolated gaseous atom. Okay. So you have one, it's a neutral atom. You take one away. You got to put in energy to pull that guy out. That's ionization. Now you come in and you have a neutral guy, and now on this one, instead of taking, you give, and it releases energy. Okay? You got to pull it out, it takes energy, you got to input energy. If you put it in, it releases energy. Okay? And that's electron affinity. pulling it out, ionization, putting it in, affinity. Okay, not infinity, affinity. All right, everybody clear on that? This is just learning the terms, okay? So make sure you underline, make sure you note, make sure you know what I'm talking about and what the specific difference is. So if on a quiz, I can ask, what's the difference between ionization and electron affinity energies? And you say one is the energy for taking an electron, ionization, and one is the energy for giving an electron affinity. Okay? One releases and one gains. One takes energy and one releases energy. Ionization takes energy into the atom, and electron affinity releases energy. Okay? You have those very clear in your mind what's going on. We'll try and talk about that some more, but you're going to have to sort of wrestle with these topics and really get them into your mind. Okay? If you don't understand them, let me know. 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 Okay? All right. Electron now loses during ionization. We're on page 111 here. Come from the orbital with the highest principal quantum number. Okay, so what does that mean? It means if it's bromine, the highest principal quantum number is your highest shell. So he's got electrons in the fourth shell. So the ionized electrons are going to be the ones in the fourth shell. Okay? And then they come from the orbitals with the highest value, the azimuthal quantum number. Okay? That just means they come from S's and P's before they come from D's. Okay, we're not going to do any ionization from D's. Okay, this is we're keeping it pretty low key here. Okay, we don't want to get into all the super complicated, complex situations or what's different in this one and that one. We're just going to do the basic rules, and I want you to learn them well so you can take them with you. So the next time you see them in chemistry, physics, whatever, in high school or college, you remember these kind of basic rules. Okay. All right. So let's look through these right here. Write the electron configuration for tin 4+, and manganese 4+. All right. So they went ahead and wrote this for you. So tin, let's find it on here. Where is 10? Let's find it here. All right. 10. Right here. So where are we? 5s2, 4d10, 5p2. Okay, so they gave you the krypton condensed, krypton, 5s2, 4d10, 5p2. So what does this tell us right here? The orbitals associated with the highest principal number, so the 5s. Take the two 5s, because we've got to get to 4+, that means we've got to remove 4 electrons, so 1, 2, 3, 4. Alright, if we were looking at 10 2+, we would take them from the P's before we take them from the S's. Okay, it's basically working backwards, guys. Alright, so what electrons we're going to lose? Okay, we're going to lose the P2 to make it a P1. We're going to lose the P1, then we're going to lose the S2 and then the S1. Okay, so we're leapfrogging backwards towards the beginning of that row. And the order of that's going to be just like you would think. P2, P1, S2, S1. Okay? So that's our final electron configuration of the ion. Look how this is written. Note how this is written. So if I ask you something like this, you need to write something like this. Okay? You could write this and then cross that out, and then write this. That was super awesome to show you that you really do understand what we got going on. Okay? But this is fine. Okay? This needs to show up somewhere on your answer. Okay? Alright, so this one. Manganese 4 plus. Where is this one? Okay. 4s2, 3d5. Okay. So it's not, on these guys with the d's, it's not just bumping backwards. Okay. It's going to lose the s's and the p's first. The 90 p's, this guy's going to lose his s's. Okay. So he's going to lose the s's first. And then after that, he loses 2 d's as well. And that first loses his 4s, which I have N4 and L0. Just simply the s's and p's come first. P's and then s's and then d's. Then it loses 2 of its d electrons, which have N3 and L2. Okay? And it looks like this. Okay? Look back through that, absorb that on your own time. Okay? Now, in the real world, you're not going to have very easily a lot of 4 plus, 5 plus, 6 plus ions just because of this next thing we're going to talk about. Okay, we talked about first and second ionization, first ionization energy, second ionization energy. All right, look at this, man. Lithium, 5.3 electron volts. Boom. 15 times that to remove the second electron. Why? Because lithium, remember we said everyone wants to get to a stable deal? Well, after you remove one, it's real easy because he wants to give it up. Okay? Remove one, he's here, he's stable. Now he says, I'm stable, I'm not giving up another one, I have exactly everything I want. I'm going to charge you 15 times as much if you want to take another electron. Now if you want to keep going, the price keeps going up. Okay? Almost doubles between second and third. Okay? So first ionization gets in here, second ionization takes in here, and third ionization will take him all the way to where he doesn't have any, which is why there's not a fourth fit, because he's out of electrons. Okay? Alright, so beryllium's not so bad. Beryllium loses, and it's 9 electron volts, and then it just doubles. Okay, so times 15 times 2. Okay, but then, where's his big deal? Whoa, almost 10, not quite 10 times as much, but 8 times as much, maybe 9 times as much. Because this one was double, because even though he doesn't like giving up electrons, okay, he likes being a neutral species. Okay, he also feels the pull to get to his noble gas configuration there. Okay? But then if you take him all the way down there and then try to make him go further, boy, he's angry about that. Doubles to 18 and then times 8 up to 153. And he's still even mad about taking a 4. Okay? So you'll see these, and I think these are a graph. Yeah. Here's our first ionization numbers. First ionization energy graph. And so what do we see? See that all these guys down here really want to lose that electron, so they're not going to charge you very much to give it. Okay? All these guys, where are they? Those are all of our stable noble gases. They don't have to do anything. That's why they're so hard to discover, because they didn't react with anything. They didn't do anything. They don't want any electrons. They don't want to give up electrons. Look how high the penalty is. So lithium's way down here, 5.38. Look at neon. To remove one electron, it's 4 times as expensive to get one out of neon as it is out of lithium. Okay? Take a look at these. Note, all the high ones are your noble gases. All the low ones are the ones that want to lose an electron anyway to get to that noble gas configuration. Okay? A lot of information to absorb here, guys, but you just need to think about it. You need to think it through. Think about why things are the way they are. All right. I've taken enough of y'all's time so far. Let's very quickly look back at our objectives, because we've got a test and then quiz on these. General structure and arrangement of the periodic table of elements. Okay. We need to talk about periodicity. Okay. We need to talk about Mendeleev. Okay. That means you need to go back and you need to correct your Asimov things and make sure everybody's got the right answers on those. Okay. They're not hard. I saw that 90% of people got 90% of the questions right. So you should be able to figure out the ones that are wrong in yours based on a number of other people. Okay, we'll get together at lunch. You're all together all the time. You can make some time, get that corrected. Okay, just make sure you get it all right. Okay. You're going to need to know groups, periods, metals, nonmetals, metalloids. I wouldn't pass up knowing some of these for the metals, anions. You need to know cations, anions, wherever that is. Anions. You need to know what a semiconductor is. Okay, a lot of vocab in here, but that's, you guys are sometimes a little bit more comfortable with that than about some of the more word problem, creative type solving problems. Okay, so take this opportunity, blow this quiz out of water. We got a lot of vocab. Okay. Now, atomic radius, you're going to need to know what that is. I might know how it gets tested, how they figure that out. You need to know that biggest and smallest. Biggest, smallest. Make a note card. The biggest atomic radius, atom, francium. The smallest atomic radius, helium. Test yourself. Make sure you know. Everything else can be deducted from there, deduced from there. Okay? You don't need to know all of this, but you do need to know these trends, right? That is, you go from lithium to neon, they get smaller. Those atomic radii shrink. Why is that? Because each one of these adds a proton, which pulls on all those electrons, and that pull gets stronger and stronger the more protons you add. Okay? Then you need to know what the shield effect is, where inner electrons sort of shield the outer electrons from that pull of the nucleus. You need to know what happens here. And again, it's common sense, but you need to think it through so you have that common sense in your brain. If you take an electron away, make it a +1, it gets smaller. Okay? Blue is the atom, yellow is the ion. Okay? If you add electrons in to go to a negative charge, they get bigger. Okay? Very common sense, but easy to get turned around. Okay? And you need there will be something like this. I promise you, there will be something like this. Okay? On the quiz, you'll have to order them, either from big to small or small to big. I'm not sure which one. I sent you some practice stuff, but I'm maybe out of time on some of this stuff. So, okay, great. Let me upload this. You'll have a bell ringer. You're at the end of the class. I'm telling you what you've already done. Sorry. All right. Have a great day. We'll be in touch. Bye.